Y'all use the recordings? Yeah. Alright, so our centripetal acceleration, AR, is equal to v squared over r. We can substitute this to find an alternate form for the centripetal acceleration. So if I substitute that, I get omega r squared over r, which is equal to omega squared r. So I have two forms for centripetal acceleration, that v squared over r, and then I also have AR equals omega squared r. Those are both identical. I'm just substituting one equation to create this new expression for centripetal acceleration. And they're both on your equation sheet, I think. Is that true? Does anybody know right off? Let me take a quick look. So you will have this equation sheet for the next exam. And as I said, the next exam, part of it very likely will be take-home from chapter 8. So there'll be 3 chapters on the next exam, 6, 7, or excuse me, 7, 8, and 9. Excuse me. So chapter 9, which isn't in your book, will be on elasticity and equilibrium. That'll be a take-home portion. Let's see, equation sheet. Oh no, it's not on there. We need to put it on there. I'll put it on there. So, let me make a note to myself. Oh, shoot. You want to see our Halloween pictures? Right quick. Y'all care? Yeah, you do care. Right. Because we had great costumes, I think. I saw Tom. They were good costumes, Tom? Yeah. Let's see. I was Gandalf, and my little boy was Bilbo. That's pretty good, right? And although, never mind. And my wife was a scarecrow, and my little girl was Dorothy from Wizard of Oz. Yeah, let's see. Oh, and my little girl made this pumpkin and painted it green like the Wicked Witch of the East. But then it all rotted, and so we said it was like the witch melting, you know, from the movie. I'm melting, I'm melting. She thought that was pretty cool. We did the trunk or treat here at Nichols. And the veterans, they had a thing out. That was fun. The kids liked it. Oh, that's something else. Anyway. Hey, Courtney. Okay, so centripetal force. As I already said, it's a term that's used to describe an already existing force. So like in the earbuds, it's a tension force. If you're driving around a car, it's a frictional force. Are there any other forces that can act as centripetal forces that you can imagine? Think a banked curve, or maybe you ever been on that ride at the fair that spins you around where you stand up against the wall and it squishes you against the wall? Yeah, right. I think it's called that, zero gravity.
Yeah, although it doesn't feel like zero gravity because you just pushed it to the wall.
You're pushed into the wall. I think you slide up the wall or something. Does that? I don't know. I haven't done it in a long time. But what are the norm or sorry? What is the centripetal force in that case? What is the force that's making you go into a circular path? The what? Right. We call that the what? The surface pushing back on you? The normal force, right. So the normal force is the centripetal force in that case. So the normal force, tension force, frictional forces, those are all really common centripetal forces. We'll work through some problems in a bit, and we'll show you how to use those to determine particular things. Okay, so in the case of the earbuds or a hand in the ball, like where you have a, where you have like a ball on a string and it's going in a circular path, the centripetal force is caused by tension. It's this force that causes the ball to change the direction. So the force tension is the centripetal force. And since our acceleration is given by v squared over r, we can calculate our centripetal force, Fr, is equal to mass times acceleration, which is equal to mv squared over r. So our centripetal force is given by this expression, which is just from Newton's second law, mass times acceleration. Here's kind of a cool thing. This is a nice demonstration of centripetal force. I've got this on this website called thespillknot.com, and they sort of sell this thing for like old people and little kids, and they show people you can carry your coffee mug or whatever on it, and you can carry it around, and it doesn't spill the coffee, and it's kind of cool. In the commercial they show like a half dozen old people carrying their coffee mugs around like this. They all have one of these things, and carrying their coffee, and it doesn't spill. And then they show like a bunch of 8-year-olds running around with their drinks, their juices. But it's kind of nifty. I've been using it. Like I just got it as a demo, but I've been using it to carry my coffee upstairs because I'm always spilling my coffee. Because if you carry a coffee mug, you know, you sort as you're walking along, you spill it on the floor, right? Because you're moving back and forth in this way, and you're actually producing forces, lateral forces, as you're carrying it around, and you just spill it all over the floor, and then the janitor comes behind you, and she's all upset. And anyway, it's a big mess. So, but in this, it takes away those lateral forces, so that you can no longer exert forces in these directions, which keeps the water from sloshing out over the sides. So see, like this, I can jiggle it around all the way, and because this has a flexible strap, I'm not able to produce those lateral forces. It's really pretty nifty. I'll pass it around in just a second so you can see. So that's one thing. That's not really related to centripetal forces at all. But if I can take this, and because of the way it's set up, I can produce a centripetal force, which will cause the cup to move in a circular pattern. Have you ever seen this? No? What's that? Yeah, it's kind of cool. So I can take this and move it around in a circular path. And what's going to provide the centripetal force, which forces the water and the cup into a circular path, in this case? Right, so I'm exerting a force, and actually there's a normal force that's pushing on the bottom of the cup that's causing it to move into a circular path. So you have to practice with this. You can zoom around. I think not were you afraid? So what you're doing here is you're forcing this into a circular path. Now, the water, like in the bottom of the path, the water wants to continue on in a straight line because of its inertia. But by pushing on the bottom of the cup, it forces it into this circular path. The spill knot. It's pretty cool. Are y'all all going to go get these? Like, I think one day at Nichols, everybody's going to have one of these. They're just be walking around, carrying their cup of coffee, and never spilling a drop. Never spilling a drop. So y'all can pass that up. Don't bring the water. All right, let's try this clicker question next.
They should sell one of those in every bar.
Yeah. They give a warning. They say that, you know, you can still knock your cup off. Like if somebody runs into it, it'll knock the cup off. But it won't spill. Try moving it around. It's I used to be a waiter. They should really have waiters with trays like this, because then, you know, you can't spill the drinks. All right, let's try this quick question. Here I have a ball that's moving around in a circular path, traveling around like this, and at some point you cut the string. Say at this point you cut the string. I just want to know which path will the ball take. Will it take A, B, C, or D? If I cut the string and take away the centripetal force. And that centripetal force is what's causing it to move in a circular path. And you also want to think about the inertia of the object. And what causes it, what happens when you cut the string. just about 5 more seconds. Still missing a couple people. Yeah, you have to, if you spin it around in a circle, you have to get it in a pretty wide circle, right? For reasons we're not going to get into. And your speed has to be just right. So if you go too slow, it'll just fall on top of you. All right. Oh, very good. So because it has this inertia, it wants to continue on in the path that it's going. And so at this instant, its velocity is in this direction. Its velocity vector is tangent to the circle. So if you take away that centripetal force, it's going to continue straight along in a straight line path. And let's try this question, and then we'll look at some old test questions in the back of the book. So let's try this question. If a certain truck can go around a flat curve having a radius of 120 meters with a maximum speed of 25 meters per second, what maximum speed can it go around a curve having a radius of 75 meters? You might not know how to do this right off, so let me give you a bit of a head start, or a jump start. So I have this object, this truck, that's going around a curve, and this curve has a certain radius, r, so it's a part of a circular path. It can go safely at a speed of 25 meters per second if it has a radius of 120 meters. And so I want to know what safe speed can it go if I give it a bigger radius, right? Thank you. You can just set it right there. Thank you. All right. Now what you want to think about is what provides the centripetal force? What provides that centripetal force? And how is it related to the radius and the speed? All right. Take a couple minutes to think about that and work on it, and I'll start working on it in a couple minutes. What force is providing the centripetal force in this case? Not the normal force, but the frictional force, right? So the frictional force is providing the centripetal force, and we know that frictional force is mu times our normal force, right? So it is related to the normal force somewhat. So our mu times our normal force is equal to our centripetal force. I'll write that down. So mu force normal is equal to mv squared over r. I know that this remains constant, right? For all it's always going to be the same for a given object that also have the same frictional force. Let's see, about 15 more seconds. Stop at 415. Okay, let's see. I think it's C. Is that right? Well, we can look at it and say, well, at this curve, which is 120 meters, so that means a nice wide curve with a big radius. The speed is 25. So with a curve with a smaller radius, is it going to be a bigger or smaller speed?
Smaller.
Right, it'd be a smaller speed because it's a tighter curve, and so you have to have a smaller speed. So that gets rid of this answer and this answer. So A and C are good answers. One of them is correct. And then I can go about this a couple of ways. I'm going to go through it first the long way, and we'll first calculate what is mu, and then we can calculate what is our new V, and then we'll do a simpler way. So the first way I could do is I could say mu times mg, which is our normal force. If we have an object that's on a flat curve, then only the frictional force is, or excuse me, the normal force is equal to the weight of the object. We'll work a banked curve in just a minute. It works out a little bit differently. And that's equal to mv squared over r. Our masses cancel, which is nice because then for these curves, the speed of your car doesn't depend upon the mass of your car. Right, so a little bitty car will have the same safe speed as a real big car. And then I can solve for mu. So that's going to be v squared over gr. Given these values that I have, it's going to be 25 meters per second over 10 times r, which is 120. And I get a coefficient of friction. This is our static frictional force. 25 over 1200. Oh yeah, 25 squared, thank you. Uh, 0.52. So that assumes a coefficient of friction between your tires and the road of 0.52. Is that a coefficient of kinetic or static friction? Static, right. Remember when our tires are rolling, the surface of the road and the surface of the tire are stationary with respect to one another. It's only when your tires are not rolling that they start to skid, and then that's kinetic friction. So this assumes that the coefficient of static friction is 0.52. And then I can take our other values. I can take the same thing. I can say mu times g equals v squared over r, just taking this expression. And now I'm solving for v. So v is going to be the square root of mu gr, which is equal to the square root of 0.52 times 10 times r, which is 75 meters. I get 20 meters per second. All right, which is the right answer. So A is the right answer. All right. Now that's kind of a circuitous way to get to the answer, because if I look at this expression, I know that this term remains constant regardless of what speed you're going at. Right? So mu Fn is going to be the same no matter what your speed is or no matter what the radius is. So if this is constant for both scenarios, then I can say that this is constant for both scenarios as well. So I can say then that mv squared over r in the first scenario is equal to mv squared over r in the second scenario. So I can get rid of those, and then it just becomes a simple ratio. So v1 was, what was it, 25 over 120. So 25 squared over 120 is equal to v2 squared over r2, which is 75. And then so v2 becomes 25 squared times 75 divided by 120, and take the square root of that. So let's double check that. That should be the same. Yeah, 20 meters per second. All right. You have several more homework questions in the homework for this chapter that deal with these types of things with centripetal forces. Well, let's look now at some of the old tests. I think I have an example in the old test. If not, we'll look at one of the others that deal with this. Or I might not in this test. Yeah, let's look at this number 14. This is on page 329. It says a boy swings a 2-kilogram stone in a vertical circle with a radius of 2 meters. The string breaks when the stone rotates at 2 radians per second. Where in the circular path does the string break? At the top, bottom, or the side? So this is what we have. We have this little boy, and he's swinging a stone around in a circle like this. So he holds a string that's connected to the stone, and he swings it around in a vertical circle like this. You know, if you swing it fast enough, then eventually that string will break because the force required to move it into a circular path will exceed the maximum allowed tension in the string. So if you swing it fast enough, or if you have a mass that's big enough, the string will break. And this says that the string will break when the stone rotates at 2 radians per second. And we want to know what tension in the string will cause it to break, and then where in the circular path does the string break, at the top, bottom, or side. You start with that first question, or the second question rather. Where in the path would the string break? Would it break in the top, in the bottom, or on one of the sides? Whereabouts would it break? Where would the force be greatest? At the bottom. Okay. Why do you think at the bottom? Okay. Well, gravity is always pulling it down, but you're thinking in the right way, because at the top, if we look at our forces, I have the tension in this direction, but then I also have the force due to gravity in this direction. All right, so both of those combined cause the centripetal force. But in the bottom, when my ball is here, I have the tension, which is in this direction, and then I have the gravitational force, which is in that direction, which is equivalent to the weight. Now on the side, it's something different. I have here the tension is in this direction, and my weight is actually in this direction. So the tension is alone the centripetal force. So at the top, I'm going to have Ft plus Fg will equal my centripetal force. But at the bottom, I will have Ft minus Fg will equal the centripetal force. As another way of thinking about this, if you remember from our chapter 4, when we did Newton's laws, we said that the sum of the forces is equal to the mass times the acceleration. This is exactly the same as what we were doing there, but now our acceleration is not a linear acceleration, it's a centripetal acceleration. So now we can say that the sum of the forces is equal to m times ar, which is m times v squared over r. So that's all that we're doing here, is we're saying the sum of the forces is equal to mass times acceleration. And when I sum the forces at the top, we just add them up because they're both in the same direction. But when I sum the forces at the bottom, I subtract them because they're in opposite directions. So now think about what would be the tension in the string that would cause it to break. If it breaks at 2 radians per second, what is the tension in the string? Hmm? Would be what now? Right. The answer to part B would be at the bottom, because the tension at the bottom is going to be bigger than at the top. You can see here, this is at the bottom, this is at the top, and so the tension at the bottom will equal to my centripetal force, which is Fr, plus Fg, which is the weight of the object. Y'all work on that for just a minute. I'm going to look at the old exams. I want to see if there's another problem. I'll be right back. Anybody have an answer yet for the tension? You have any clue where to go from here? Any clue at all? It's okay to not have a clue. You have any clue? What do you have an answer? Okay. What you want to do here is you want to recognize that Fr is equal to mv squared over r, which is the same as, you remember, m omega squared r. Those are the identical expressions. And then solve for Ft. No, remember our SI unit is radians. So as long as you're using values for omega, then you'll just use that radians per second. Now, if you want to calculate it in this way, where you're using V instead of omega, then yeah, you'll need to convert it to meters per second, where you multiply times the radius. Either way should be fine. Now, don't forget, mg is our weight of our object. 24. Anybody else get that? 24 newtons. Okay, let's see. Our tension then, this is what we're trying to solve for, is what is the maximum tension that we can allow for. That's equal to m omega squared times r plus m times g. The sum of those forces will give us what is the tension in the string. This m omega squared r, that's everything's 2. So 2 kilograms, 2 radians per second squared, 2 meters plus 2 kilograms times 10. 2 times 4 is 8. That's 16 plus 20. I get 36 newtons. Isn't that right? 8, 16. Yeah.
I use V squared over R.
Okay, if you use V squared over R, that's fine, but you have to be careful. Let me erase this. If you use V squared over R instead, we say m V squared over R plus mg. You have to recognize that V is equal to omega R, so V is actually 4 meters per second, because omega was 2 and the radius is 2. So then that's going to be 2 kilograms times 4 meters per second squared over R, which is 2 meters plus 2 kilograms times 10 meters per second squared. So the 2's cancel. 16 plus 20 are 36 newtons. It's fine to use v, that's fine, but you need to make sure that you convert your angular velocity to a linear velocity. While we're here, let's do this other kinematics problem. Where was it? Since we're just coming off of kinematics. Let's try this one. I'll zoom in a little bit. This is on page 326. Merry-go-round rotates from rest with an angular acceleration. How long does it take to rotate through the first 2 revolutions? And then how much time is required to travel through the next 2 revolutions? It says you need the quadratic equation, but don't solve for t, just set up the appropriate equation. So just get up to where the quadratic is and set it up with the right values. While y'all are doing that, I'm going to go ahead and hand out your exams. And I'm not going to hand back the forms that you took, but I'm going to pull up the answers for the multiple choice. So you can take just a minute. You can mark off your multiple choice, because they're not marked up here. Oh, that was a mistake, in and out. Oh, I'm sorry. All right, let's try to work through this problem here. So if it starts at rest, that tells me that what is what. If it starts at rest, that's talking about what? Not v naught, but omega naught. So omega naught is equal to 0, and then it has an acceleration. Remember, that's not a, but that's alpha, which is 1.5 radians per second squared. And I want to know the time for it to travel through theta equal to what? Okay, yeah, 2 revolutions. But since everything else is in radians, I'm going to go ahead and convert that to radians. So that's 2 times 2 pi, or 4 pi radians. All right, this one's pretty simple. How much time does it take to rotate through the first 2 revolutions? So yeah, just say theta equals omega naught t plus 1/2 alpha t squared. And then I say 4 pi equals 0 plus 1/2 of 1.5 t squared. And then I just solve for t. So that's 4 pi over 3, the square root of 4 pi over 3. I never found my pi out here. I get 2 radians, or 2 seconds rather. So it requires 2 seconds to go through the first 2 revolutions. Alright? Now how about the next one? How would I solve for that? To go through the next 2 revolutions. So I think we'll come back to this, guys, and I want to show you the key, and then we'll come back to this on Wednesday. I'm sorry, that's like a cliffhanger, right? Is that a cliffhanger? Yeah, and we'll come back to part B. I'll have to make myself a note. So I want to show you the solutions. So guys, on that exam that I handed out, the multiple choice, as I said, aren't marked, but I'm going to pull up the key for it right now. So please just take a moment to go ahead and mark them. I'll put up a key later, but this is your exam. There were only 13 multiple choice, but as with the last exam, I counted them like 15. So really there were 2 invisible questions that everybody got right. Okay, so those, I think there are, you can mark the ones that you got incorrect.